we are looking for the double integral of the natural log of x squared plus y squared over the square root of x squared plus y squared dx dy. And the region that we're integrating over is this region here. R is the set of all x and y coordinates such that x squared plus y squared is less than or equal to 4, but greater than or equal to 1. So this is the second video that we're doing on double integration in polar coordinates. Let's just dive straight in. If you're not sure what's going on, check the link in the description to the first one and let's just go straight for it. So first thing we're going to do, as always, guys, is draw the region. Okay, guys, so I've just drawn the region down here. This is called an annulus or a punctured disc. It's just, of course, two circles. So the equation of the inside circle is, of course, x squared plus y squared equals 1. And the outside circle, the bigger one, is of course x squared plus y squared equals 4. And of course that is a circle that has a radius of only 2 because it's x squared plus y squared equals 2 squared. So that's why this is here. And we're looking for the x and y values between 1 and 4 when you square and add them together. So this is the interval that we're looking at. Next thing we're going to do is just convert it into polar coordinates. So it's no good doing our integral, double integral as it is here. One, it looks really complicated, so that's not very good. But two, if we convert it into polar coordinates, the limits will be very, very nice because, as I said in the previous video, the limits in Cartesian for something like this are very, very, very confusing and difficult and complicated and all that stuff. So we're going to convert into polar coordinates. As a reminder, remember, x is r cos theta, y is r sine theta, and when you change dx dy, that's going to become r dr d theta. So these are the things that you just need to basically just know, super important stuff. So now we can actually rewrite the integral. So let's do it right now. So we've got the integral, double integral, and we'll fill the limits in at the end. But we've got the natural log of, well, x squared plus y squared. So you can either replace x and y with r cos theta and r sine theta, and of course you square them and realize, but you probably, or hopefully you already know, in polar coordinates, x squared plus y squared is actually just equal to r squared. That's just a consequence of what x and y actually are. So I'm just going to directly place it with r squared there. And then I'm going to divide it by what? Well, again, x squared plus y squared is r squared. And so we're just taking the square root of that. So, of course, we've just got r on the bottom there. And again, dx dy is going to get replaced by r dr d theta. So you can already see a lot of stuff's going to simplify and it's going to be quite nice. But now we need to deal with the limits. So remember, dr is first. So that means that the inside, the rightmost integral, the limits of that are going to be the r limits. Remember, the r is a value that is telling you the distance from the origin that a point is. So we're not talking about left and right and up and down. We're talking about the proximity of each point from the origin. So we can see that the inside or the smallest value of r in this interval here is 1 and the largest value is 2. So those are our r limits. And then we've got d theta on the right here. So the outside integral is going to be in terms of theta. And of course, because we're going all the way around the circle, 2 pi radians around, we're going from when theta is 0 up to when it is 2 pi. So these are our limits here. Okay, cool. Now we can, work towards simplifying this thing, and it's not going to be too bad. I think that actually the difficult stuff is probably in the past. It's behind us. So let's simplify the integral before we actually integrate it. So we can notice that the r's cancel out. They're just gone. And the natural log of r squared, it's much nicer to write this as 2 times the natural log of r dr d theta like that. One more thing I'm going to do is I'm going to take the number 2 to the outside of the integral, and I'm going to take it to the outside of both integrals because it's completely fine to do that. So put a big 2 on the outside, integral from 0 to 2 pi, integral from 1 to 2 of the natural log of r dr d theta. Cool. The natural log of r is actually not very difficult to integrate. You just use integration by parts. I'm going to assume that you guys have got no problem doing that because it takes a little bit of time. Some people even memorize the integral of the natural log of r or the natural log of x or whatever. And I happen to also be one of those people that memorizes it. So just to be clear, if you don't know how to integrate the natural log of x or the natural log of r, all you do is you do integration by parts on it, okay? And what you will end up getting is r times the natural log of r minus r. Okay, that's the integral of the natural log of r with respect to r. So we've got our limits, 1 and 2, d theta on the outside there. And of course, we just keep working through. So 2 integral from 0 to 2 pi. We can now plug our numbers in. So we've got 2 times the natural log of 2 minus 2 minus 1 times the natural log of 1. And then I'm not doing the bracket, so this is a minus minus, so it ends up being a plus 1 there, d theta. Hopefully this stuff is not really the difficult stuff. Again, I think the difficult stuff is probably behind us. Okay, so we've got 2 times the natural log of 2. The natural log of 1 is 0, guys, so that's just gone. And we've got 2 times the natural log of 2 minus 2 plus 1. That's 2 ln 2 minus 1 d theta. And this is super easy to integrate because, of course, all we do is just times each term by theta because it's a constant and another constant. So it's just going to be 2 times the natural log of 2 times theta minus theta. And you could even factor it out and just have 1 theta on the outside there. All right, so we've got 2 times 2 ln 2 times 2 pi minus 2 pi, and we can actually see that the other term will just be 0. Okay, so the other term is just going to be 0. So we've got a closed bracket there, minus 2 times, both of these terms are just 0, so we don't need to really worry too much about them. And here we have got 2 times, and then what is this? So in the brackets here, we've got 2 ln 2 times 2 pi. That's 4 pi ln 2 minus 2 pi. And this is just going to be 8 pi ln 2 minus 4 pi. And that's going to be the answer. If you want, you could factorize it. You could take a 4 pi out. So if you want to, you can go, this is 4 pi 2 ln 2 minus 1 or something like that. Or even you could go even further and you could say this is 4 pi 2 ln 2 is ln 4. So if you want, you could, there's lots of ways you can write it, right? But like any one of these answers would be a pretty valid answer. So any of these, they're all the same. They're all equivalent to each other. Any of these, even the one above, would be pretty satisfactory as an answer. So that's how you do that. And so, of course, you can see quite a difficult looking problem, but it's not really too bad when you convert it into polar coordinates. Stay tuned for more videos on double integrals in polar coordinates. Thank you so much for watching. As always, I highly appreciate it. You guys know that, and I'll see you in the next one. Cheers.